present here. The topic is strength studies on fiber reinforced concrete with partial replacement of plastic waste as coarse aggregate. So as everyone knows, concrete is the most widely used man-made construction material, and it is a mixture of cement, water, coarse aggregate and fine aggregate. So if you take generally aggregate is a major part of the concrete. So in order to take that aggregate, we are quarrying the many, we are destroying our many rocks that is from granite and limestone they are extracted. Because of this quarrying and processing, what happens is this major environmental, it causes major environmental problem. So we have carbon dioxide emission is more, and we all know that it is a major threat to the environment. And this environmental effects is mainly caused because of the mining of rocks. So our idea is that we can minimize this environmental effect by replace with plastic waste aggregate in the coarse aggregate. So that is the idea behind this paper. So plastics use is day by day, it is increasing day by day, and the generation of plastic is also more. And what they are doing is that they are recycling this plastic again and again, and again materials are produced from this recycled plastic. So moreover, when the plastic is again and again it is recycled, the strength of the plastic is getting reduced. So basically it goes as a landfill. So our idea is that we can use that plastic. Why don't we use that plastic in the coarse aggregate by partially replacing this coarse aggregate, and how to determine the strength properties of the material. So this is the basic idea behind this paper. So apart from that, we have used this steel fibers also. So this steel fibers, if you take this concrete will contain the many fibrous material, and because of the steel fiber, the structural integrity of the concrete can be increased. So moreover, when we use the fiber, it will control the cracking in the concrete. And if you take many types of steel fibers are available in the field, but here we have used zigzag shaped steel fiber, so that it has been proved in the literature that this zigzag shaped steel fiber will give adequate bonding between the materials. So as I told earlier, so this recycled plastics were used to prepare this coarse aggregate, and because of this, the reuse of plastic when we are using in the construction field, it reduces the environmental effect of plastics also. And moreover, when we use this plastic waste aggregate in concrete, automatically it becomes an economical part. But when you take any case, 100% replacement of this natural coarse aggregate is not feasible. So we are going to do it with a partial replacement at various percentage. So the main objectives of this study is that to optimize the compressive strength of concrete by partial replacement of coarse aggregate with plastic waste aggregate, and to determine the variation of workability of concrete, and also to examine the various engineering properties of the concrete by replacing this plastic waste aggregate partially. So if you take the materials, so here we have used ordinary Portland cement of 53 grade cement, since because it will provide a higher strength even with lesser quantity of cement content. And fine aggregate, we have chosen the M sand because it can provide high concrete strength when it compared to river sand. And coarse aggregate, here this is the main one which contributes to the strength of the concrete. And steel fiber, as I mentioned earlier, so in order to resist the shrinkage and cracks, we have used the steel fiber. And again, the plastic aggregate is going to be that plastic waste aggregate. And if you take in many literatures, they have used this plastic waste separately and steel fiber separately. And the combination of steel fiber and plastic aggregate was not found when we reviewed our literature. So we thought to combine these two things, and we made an attempt. So this is the steel fiber what we have used in this experiment. So this is the one you can see that corrugated shape, that is the steel fiber will be of zigzag shape. So this will help to fill the cracks in the composite member. And this is the plastic waste aggregate what we have used in this particular study. So this is a compound of polyethylene terephthalate, and in concrete application we are used as this plastic waste aggregate. And if you take in the methodology, we have done the literature survey, and the materials has been collected, and then preliminary tests were performed then we have done our mixed design as per our IS codes and BIS standards. Then specimen has been casted and demolding and curing and testing of that specimen and result analysis and final conclusion and recommendation. So if you take the mixed design, so this has been done using based on BIS and grade designation is we have used our M30 concrete and type of cement is OPC 53 grade and nominal size of aggregate is 20 and minimum cement content for M30 is 320 kg per meter cube and water cement ratio what you have adapted here is 0.43 and manually we have placed this concrete and the mixed ratio what we have got is 1 is to 0.75 is to 1.5. And what we have done is that we have replaced, if you take in the literature, they have found to be that some 15 percentage of 10 to 15 percentage or plastic waste, if you replace, some strength can be obtained. So this is what is found in the literature. So we want to proceed still further at which amount of plastic content we are getting an optimum value. So for that person, for this particular coarse aggregate, so if we replace it with 5% of plastic and the 10% of plastic aggregate in coarse aggregate and 15% of plastic aggregate in coarse aggregate. So this is what we have obtained here. So total will be 3.73 kg. So in that, if we have taken as it is 1.5 part of coarse aggregate divided by total part is 3.25 into weight of 1 cube is 8.1. So accordingly, we have got these values for plastic content. And for each and everything, we have added 3% of steel fiber of total weight of concrete, that it comes to be 240 grams of steel fiber. So we have added that also in this particular thing. And we have casted our cubes. You can see the cubes. We have casted our cubes, and then this cubes has been cured, and the testing has been done in for 7 days, 14 days, and 28 days. And then you can see the cracked specimen after the testing also. And the analysis will be that you can see here for if 7 days curing for conventional concrete is this 18.9. And if you replace it with 5% of plastic, you can see that 15.56 and 10% it is 13.77 and 15% it is 9.77. So it shows that there is a decrease in compressive strength. So even for if you take for 14, we have to take it in row wise. That is for 14 days curing also, we can see that for 5% of plastic, the compressive strength is 19.11. And for 10% it is 16, and for 15% it is 11.12. So we can see there is a decrease in trend of compressive strength. So from this, what we are concluding is that the reduction in the compressive strength was monitored when compared with partially plastic replaced concrete. So it means what the generally that thing is that the degree of workability is equivalent to plastic aggregate as per the IS code, but what is that is the compressive strength is getting decreased. So if the compressive strength is getting decreased, we cannot use this type of partial replacement of plastic based concrete in load bearing structures. Further, we can use it in non-load bearing structures. So if you take in a building, so 20 to 30% of application of concrete in building is non-load bearing structures. That is even for, we can use this for filling and finishing. So in such cases, we can use this plastic-based aggregate in forms of coarse aggregate. So this type of partial replacement will be very well suitable for PCC roadworks or pavement, floor slab, and even for other non-structural members. But it should not be used for it should be avoided for any load-bearing structures. And these are the references we have seen here. Thank you. Any queries, sir?
Yeah, you can go to the conclusion slide.
Yeah, yes, sir. Yes, sir.
Okay. Is there any basis why you started only from 5%?
Sir?
You have started from 5%, 10%, 15%. Are there any literature
yes,
that
sir.
you should not take anything less than 5%?
We can take less than 5% also. That after that further we can do it. But in the literature they have given that no optimum percentage is obtained. Say up to after 20% or after 15%, the strength will get reduced. So this is what they have given in the literature. So
Okay. Have you
we
done
want
any
to.
cost analysis? Have you done any cost analysis?
No, we haven't done any cost analysis as for now, sir.
Okay, you can go to the previous slide.
Yes, sir.
Yeah, just once. Yeah, you see, in 15% plastic, uh, after the duration of 14 to 28, you could see there is an increase in your compression strength. Why is that?
Pardon, sir. So you're asking that why it is getting the compressive strength is getting increased when you see in column wise. Am I
Yes,
correct? Your
yes,
question is
yes,
correct.
yes.
Okay.
Specific 15%, because 5 and 10%, after 14 days, there is no much change in the conventional concrete and your reinforced concrete. But once you go to 15% plastic, you see that constantly there is an increase in compression strength,
Yes, sir. Yes,
though
sir.
not phenomenal as good as 5% or 10%,
Yes,
but you
sir.
could see that there is an increase. Is there any particular reason?
No, it's not any particular reason is there, sir. It shows that if you take in days for casting, so general case is that for 7 days of casting, the strength we should attain is 65%, and after 28 days of casting, it should attain the 99% strength. So as you have seen that, it reveals that in case of if you replace it with 15% of plastic waste, your compressive strength is getting increased. So it shows that our cost can be minimized. So we can replace that coarse aggregate with 15% of plastic waste aggregate. So that's how we have to conclude it, sir.
Okay, okay, okay.
Any other
Thank you.
queries, sir?
No, thank you, thank you.
Okay, thank you, sir.
Thank you, ma'am. Thank you. Sir, shall we ask next person to present?
Yes, yes, yeah. You go ahead,
Yeah.
go ahead.
Okay. Uh, Mohan, sir. Mohan Anakia, sir. Are you ready with your
Yes, sir. Sir,
presentation?
I'm there, sir. I'm there, sir.
Okay, sir. Just turn on our video, so and then present your slide.
Sir, my video is visible, sir.
Yeah, now it's visible.
Yeah, I'll share the screen. No, one second.
Okay.
So my video is visible. PPT is visible, sir. Hello,
Yeah, it's
sir.
visible now, sir. Yeah, it's visible now.
Yeah, yeah. I'll start. Warm good afternoon to one and all present here, and a warm thanks to Sairam College for conducting the third international conference on material manufacture and mechanical engineer for sustainable development. So basically, my topic is on like I'm a full-time research scholar in SRM Institute of Ramapuram under the guidance of Dr. TCS Madhavi Madam, Professor and HOD. My research topic is on textile reinforced concrete. Whereas a new development in India, the over
Mohan, you can be slightly loud, slightly
yeah,
louder.
yeah, one second. Now it is audible, sir. Hello, sir.
Yeah, yeah, yeah. Good, good.
Yeah, okay, fine. Yeah, my research topic is on textile reinforced concrete. If today's presentation will be on development of binders for textile reinforced concrete as a part of my research work. So as of now, nearly 45 to 60% of building construction work are related to reconstruction or repair works. For past 2 years, the past 20 years, the strengthening of executing structure has been a great task. So before development of textile reinforced concrete, the researchers found comfortable with FRP, the fiber reinforced polymer, as FRP as FRP was found to be promising element in the field of strengthening work. Uh, the main advantage of epoxy is epoxy can yield to high strength, whereas the same disadvantage yield strength due to use of chemical based resins. The same thing has been become a drawback in the use of epoxy. Due to this type of drawbacks, due to this type of drawbacks, the first due to this type of drawbacks, they replace the epoxy with new material with inorganic cementitious binder, namely known as textile reinforcement. The textile reinforcement is nothing but textiles fragments are rolled in different multi different direction, parallel and perpendicular, to combine it to form a mesh type structure. As in the figure it indicates, it's a mesh type structure. It is used for strengthening the executing structure. So when it combines with a cementitious binder, the textile reinforcement process high tensile strength. So the my topic is mainly focused on development of cementitious binder, and it is a research gap in the textile reinforced concrete. So for past 20 years, since the development of textile reinforced concrete, more of the researchers are not concentrated on development of strength for the inorganic cementitious binder, which is a major gap where, through the literatures have been found out. So textile reinforced concrete has been called by many names such as textile reinforced mortar, fabric reinforced concrete matrix, mineral based composite. In India, it is generally known as textile reinforced concrete. In Chennai, SERC was the first one to use textile reinforced mortar. In SERC, they developed a toilet panel using textile reinforced mortar. The material used in cementitious binder are aggregate size finer than 2 mm. So there are different types of textile reinforced concrete meshes are available, namely glass mesh, carbon fiber mesh, POB, basalt. In India, as per now, glass and fiber mesh are readily available. And in my research topic, I've been adopted AR glass fiber mesh. So the overview of textile reinforcement is, it is very suitable for renovating the reinforced concrete work. It can solve realkanization or reprofiling or reprofiling the executing concrete structure or reinforced structure. Strengthening of placements are provided by bonding TRC to placement by cementitious binder. So advantages when compared with FRP, the advantage will be like low cost, easily earned to any shape, better performance under high heat, applied easily, and no chemical products are used. So you can compare the size of as a single yarn of textile with our human hair. It is basically lesser than the human hair. That is 7 to 27 meter. That is lesser than the human hair diameter. So my major objective of the research is to develop to develop multi-purpose textile reinforced concrete, and to prove it is alternate to the FRP, and it is and to prove it is alternate to FRP, and it minimize the use of steel in retrofitting and repair work. And today's topic is about system. It's one of the major gap which has been found out, and to increase the sustainability. These are a few literature works which have been collected from 80 literatures. So here, the literature work states about the textile reinforcement yields in two types of failure. One is debonding, and the other one is intersurface debonding. So some of the researchers are found to be based upon that debonding and the cracking, for instance. So I'll just click on this literature and summary of literature. As I said, there are major two defects has been arrived. One is slippage and debonding of textile fragments, and under any high load, the increase in stiffness has been achieved with the TSU and compared with FRTS. So slippage under debonding is nothing but when we soak with the beam surface, when it's acted along the load, the fibers may hatch out from the cementitious layer. So it is known as slippage or debonding or delamination of the textile fiber. So for this research work, we are adopted M40 grade of concrete, and water to binder ratio is 1 is water sorry, binder ratio of 1:3, and water to binder ratio of 0.4. Three types of binder has been found out as of now. Using we have been named as a conventional, modified binder 1 and modified binder 2. In conventional binder, all conventional material, that is cement and fine aggregate, generally we use passing through 4.25 mm, but in this case we adopted just 2 mm passing through 2 mm fineness, so it is more fine when compared with the cement. And for modified binder 1, similarly, in order to achieve the great strength, higher strength, we implemented more silica, that is the major component for the increment of synthesis calcium and silicon content in the concrete. So in order to implement the more strength, so we replaced, like we taken as cement quartz powder, silica frame, and similarly for modified one, cement 50%, GC plus 50%, on quartz powder, silica frame, and fly ash. So these are the casting photos. We are totally, as per IS, we have been casted 3 sets of cubes for 7 and 28 days. The cube size is 17.6 and 17.6 mm. These are the cubes. Cubes, and these cubes are done only for compression due to COVID pandemic. We cannot concentrate on more on this, but the work is going on further. So as of now, we are just displaying the cube results. So these are the breaking patterns of the cube. So we can see that all the cubes are failed until their crushing. So when compared with the conventional and modified 1 and modified 2 was shown far incremental strength when converted to conventional binder. The increment of, so these are the comparison of the strength for M1C and M2, and this is for comparison with the M1 with the C and M2 with the M1 and M1 with the conventional binder. And comparison, the modified binder 2 was found to be increased nearly 62.5% for 7 days. It also shows an increase in compressive strength for 39.4 when compared with the conventional binder. Similarly, when modified binder 1 showed increase in strength 28.8 and 11.4 for 7 and 28 days when compared with C, it was 28 and 24 days. That's it, sir. Thank you, sir. Thank you
Yeah,
for
you
the
can,
opportunity.
yeah, you can stay with the result. Yeah, go to the result.
Yes, sure, sir. Thank you, sir.
Rather than just giving the quantified values. So,
Okay,
can you
sir.
explain why it has done 62 by
Yes, sir. Yes, sir. Sure, sir. So as I said, for increment of strength in concrete, the major two components are CaO3 and SaO2, sir. So the particle, that is aggregate which have been adopted, are more rich in calcium and silica, sir. So this is the
Mm.
reason where the both binders stands highest strength when compared to conventional binders, sir. So as of now, the research has been carrying out. So in future, like as of today, we are planning to go for SIM analysis and HIDOX
Mm.
to find out why the strength has been increased. So my statement will be like use of this SaO3 content and CaO3 content material, the strength has been increased. This year.
Can you just conclude with only the characteristics of compression strength, or should any other characteristics of your concrete should be included in your study?
No, sir. Like as of the today's presentation is only on compressive strength, sir. So we did more of the strength after the pandemic. So it's going on, sir. But for a conference, I just published with this paper. So they said like
Oh,
apart from this, nothing should be displayed. So I stopped up here, sir.
okay. Thank you. Thank you.
Yeah, sure, sir. Thank
All
you,
the
sir.
best.
Thank you. Yeah, thank you, sir. Thank you, sir.
Thank you, sir.
Thank you, sir. Thank you for the opportunity, sir. Thank you, sir.
Uh, Mainak Saha, sir, are you ready?
Yes. Yeah, yeah,
Now,
yeah.
now you can
Yeah.
present.
Yeah, yeah. Just a second. Yeah, is the presentation visible?
It's coming, sir. Yeah. Now it's visible now.
Yeah. Yeah. Okay, okay, okay. Thank you. Yeah. Okay, so very good afternoon to all of you. So today I, Manak Saha, am going to briefly discuss about the tensile creep deformation behavior of rod single phase gamma TIAL. Now this is a single phase FCC alloy. And here what I am going to explain is as follows. That is, firstly, I will be speaking on the novelty of the present work. So this alloy, the gamma TIAL, has been So the gamma TIL has been studied extensively by Hayes and Martin, by the work of Hayes and Martin. It's back in, it's a work long back in the 1970s. But then there were a few things that were missing in that particular work. The first of all, the major claims that were made by that particular work is as follows. That is, the rod single phase gamma TIAL alloy does exhibit tertiary creep between 760 and 900 degrees centigrade with stress levels of 69.4 and 103.4 MPa. Now, this was one of the major claims. Now, the second claim was that there is no steady state creep which was observed at 832 degrees at a stress level of 69.4 MPa for both interrupted and uninterrupted tests. Now, when I use the word interrupted, it was so in the literature it was mentioned, in this particular literature by Hayes and Martin, it was mentioned that the interrupted test the test was interrupted at 2 strains, that is 0.18% strain of the total strain to failure, and at 0.5% of the total strain to failure. Now, this was the interrupted test, and the uninterrupted test, which was done till the fracture. And the third claim was that the gamma TIL alloys do not exhibit dislocation creep at 760 degrees, 832 degrees, and 900 degrees between these stress levels, 32 to 345 MPa. Now the novelty, this forms a novelty of the present work, because the present work mathematically tries to review that whether the claims are really true or not. I mean, is that really the case? Okay. So in order to explain this, firstly, the creep activation energies have been determined. So these are the two plots. So first of all, this is the strain rate. Okay, the strain rate epsilon dot. This is a strain rate, which is plotted as a function of 1 by T, where T is this temperature, where temperature is in Kelvin, and the other one is the Shelby-Dawn plot. Okay, so that is the Shelby-Dawn parameter. It's basically coming from the Shelby-Dawn parameter. We can, this is the reference which gives the basis for the Shelby-Dawn parameter, and that is the temperature compensated time approach. And based on that, we can easily see that the creep activation energy, which is basically nothing but the slope of this particular plot. Okay, so the slope of this long strain rate versus 1 by T plot. We find that in the first regime, it is coming out to be 423.9 kilojoule per mole, and very still 409.82 kilojoule per mole in regime 2. Now, secondly, the regimes 1 and 2 seem to be independent of each other. That is, they do not have to happen in a sequence. Okay, they can be happening. Their occurrence is independent of each other, rather to say. And thirdly, the transition temperature, which is the most important here, is exactly observed at 838.11 degrees centigrade in both the approaches. Okay, in both the cases, we find this is the transition temperature. But now, when we go to a higher stress level, 103.4 MPa, it is observed that the creep activation energy decreases from 423.92 to 367.77 in regime 1, and in regime 2 again it decreases to quite a bit, to about around 377.68 kilojoule per mole. Whereas again, now the regimes, the regimes 1 and 2 seem to be sequential. Why? Because there is no discontinuity in the slope where at the transition temperature, and the transition temperature is found out to be equal to 825.90. I mean, it's also quite decreased when we go for higher stress levels. So with this now, I'll be with this approach. Now, at different stress levels, 69.4, so all these stress levels and all these temperatures, 760, 832, 900 degrees, all have been taken from the work of Hayes and Martin, and wherein mathematically the activation energy has been found as follows. That's what interestingly we can observe. So this is the creep activation energy, and this is the components of the creep activation energy, because so the QGB is the creep activation energy at the grain boundary, and the QL is the creep activation energy for the lattice, as you can see very clearly. So what interesting observation we can see, and this has been calculated now from this total Q, the QGB and QL have been calculated using Ashby's approach, and a very good the formula for calculating such components of Q can be easily found in this particular work. So paper very long back, but this definitely provides a lot of inputs about calculating the value of creep activation energy. So from this, the interesting observation that we can get is as follows. That is, at 832 and 900 degrees, with the increase in stress level from 69.4 to 103.4 MPa, there is a decrease in the apparent creep activation energy, but the reverse trend is observed in 760. That is, in other words, what I mean to say is that when I increase the stress level from 69.4 to 103.4 and at 760 degree, we find that the activation energy, instead of decreasing as it is found to be decreasing in 832 and 900, it is increasing at 760 degrees. Now, this is some observation which is very, very interesting. But of course, now this requires extensive microstructure analysis, which is beyond the scope of discussion today. But definitely, this kind of work is going on. So with this now, let's discuss about the creep mechanisms. Okay, so mathematically, how do we arrive at the creep mechanisms? So we can arrive using this particular approach. We can plot the minimum strain rate, take the logarithm of the minimum strain rate, and take the logarithm of the stress, and then and then for the 3 different temperatures, 760, 832, and 900 degrees, we can have this particular plot. And from this plot, we can easily find out the stress exponent. The stress exponent can be found. It's nothing but the slope of all these plots at different regimes. So what we can find out is that that TR1, this is the first, is a TR1, which is equal to 44.69 MPa. This can easily be found from, when we extrapolate this data and find out the logarithm. It's in logarithm, so it's in 44.69 MPa. The plot suggests that there is a transition from dislocation glide control creep to dislocation climb control creep. And similarly, for the second case, wherein we are having at around 832 degrees, we find that again the transition temperature is the transition stress is slightly higher, 66.68 MPa, where there's a transition from the dislocation glide control creep to dislocation climb. But however, there is a minor transition at TR3, and the stress exponent here and here, they do not vary to a huge extent. So definitely no such statement could be made for the TR for the transition, for the TR3 transition. But now when we look at the 760 degrees centigrade, wherein we find that we are having the transition temperature, the TR4 is comparatively at much higher stress levels at around 270.46 MPa. There is a transition from dislocation climb to dislocation glide control creep. And the basis why I'm saying that based on the stress exponents, there is a transition from glide control to climb control creep, or from climb control to glide control creep, can easily be found from these references. So based on that, so now we are clear with 2 things. That is, first of all, we know about the creep activation energy at different stress levels, 16.4, 100, and 103.4, and at each of the 3 different temperatures, 760, 832, and 900. But now the thing is that, and we also know about the creep mechanisms there. But we have some rough idea. Obviously, the microstructural investigation also has to be supplemented up, but that has not been provided here. So, but then once we know about the creep mechanisms, so get an indication of the creep mechanisms. So what we need to know is the creep life, because that is something which every material has to have. It is always desirable to have an engineering material with a very, very high creep life. Otherwise, the material cannot be used for engineering applications, and especially at elevated temperatures. Right? So in that case, what we do, there are 2 very common approaches. The first is the Larsen-Miller parameter approach, and and as you can see that there we basically plot the rupture time in hours in the logarithmic scale as a function of 1 by t. But definitely I have taken a 10 to the power 4 just in order to scale these values up. Otherwise, this will be coming in terms of some decimals. So 10 to the power 4 by t, and obviously t is in Kelvin. So this becomes per Kelvin. So what we observe is that with an increase in stress levels from 69.4 to 103.4, the creep life decreases between 760 to 900 degrees centigrade. Right? And then similarly, this is another approach, is the Manson-Hafford approach. And here in this approach, again, what we can say is that with an increase in temperature from 760 degrees to 900 degrees, the creep life decreases for stress levels of 16.4. And as you can very clearly see, that is 16.4 here, and 100 MPa and 103 MPa. Okay? So definitely. So we now have some indication of the creep life as well. But then there is another phenomena that needs to be addressed, and that is nothing but the creep rupture mechanism. So the creep rupture mechanism can easily be addressed when we look at, if we have to use the other parameter, there is another approach, mathematical approach, that is the Monkman-Grant approach. And based on that approach, what we can say from this particular plot is as follows. That is, the predominant creep rupture mechanism is a power law breakdown at 760 to 832 degrees. Okay, so both these cases, where why, and the reason why I say this is because the mg exponent, this can easily be extracted from this particular plot, is in both the cases 760 and 832 is found to be less than minus 1.4. And in the second case, we see that there is no power law breakdown at 900 degrees because the mg exponent, Monk-Grant exponent, is nearly equal to 0.4, and that is comparatively much greater than minus 1.4. I'm sorry, I have to put a negative sign here. I'm sorry for that. So yeah, so it's more than minus 1.4. So definitely, so in that case, definitely we can now get an indication that there is a power law breakdown at these first two temperatures, 760-82, but then there is no power law breakdown at 900. But again, this is also subjected to further microstructure analysis as well. So with this, what I this present work concludes of a bit of things. That is, the creep life between 760 to 900 degrees and between stress levels of 69.4 and 103.4 MPa is dominated hugely by the tertiary creep. Okay. Then secondly, we say that so earlier the claim was as follows: that is, there is a steady state creep which is observed at 832 degrees for 69.4 MPa for interrupted tensile tests, but definitely we do not see. So based on the activation energy and based on the stress exponents, we can definitely say that there is no steady state which is observed at that particular temperature and that particular stress level. So even for the interrupted tensile creep tensile tests, so tensile creep tests. Then thirdly, the dislocation creep, as I have discussed very in one of the earlier slides, the dislocation creep tends to the main deformation mechanism for these alloys at ththese temperatures, and 768, 32, and 900, and between 32 to 345 MPa, where although the dislocation creep may be in the form of dislocation glide controlled or dislocation climb controlled, but definitely this mechanism of this creep mechanism was not at all discussed in the earlier work. Okay, and then this is a very new work. It's going to be totally in a new direction. It's not at all discussed in the major work. Okay, and in all the other subsequent works on gamma TIAO. Then fourthly, the most importantly, is that the creep life of the alloy decreases due to the onset of the creep rupture, which I have discussed in the earlier slide, with the increase in the stress between 69.4 to 103.4 and at temperatures between 760 to 900 degrees. So with this, I would like to conclude my presentation for today. Thank you.
You can go to the previous slide.
Yeah, sure.
Why do you always restrict between 69.4 and 103.4 megapascals when you could have the dislocation creep between 32 to 345 megapascals?
Yeah, okay. So definitely. So within that 32 to 345, and like so this has been taken from the earlier literature. So the literature, what I mentioned is 32 to 345. They say that the dislocation creep can be observed. But now 69.4 and 103.4, they have provided a list of what to say, the activation energies, as well as they have also provided the data. I mean the other data, like the creep rupture data, the stress exponents and all.
Okay, what is the application of your material? Where is it used?
Generally, it's a high temperature material. Mostly, it's used for aerospace applications, aerospace industries.
In which component?
Especially in the turbine engines, gas turbine engines.
Gas turbine engines. What is the temperature it would be? Do you think that at 900 degrees centigrade, if it is going to the tertiary creep, it will work well there?
No. That's what. So in that case, I mean definitely. I mean this material, first of all. So the at present is that to make the use of such a material in such aerospace industries. I'm not saying that this is currently being used there, but then this material has. I mean it has been potentially, like, people have been saying to use it. I mean it has not been used there, but they are trying to use it. I mean in the gas turbine engines, not at present. Not using it at present. It's not possible.
Okay. Okay. Thank you.
Thank you, sir.
Thank you, sir. Thank you. So we have one more person. So Hamadri, sir.
Sir, shall I present, sir?
Yeah, are you ready?
Yes, sir. My student will join. You can accept, sir.
Okay, sir.
Okay.
You may share your screen, sir. Sir Hamadri, sir, are you there? Mr. Hamadri, sir.
Sir, yes, sir, I am there, sir.
Okay.
2 minutes, sir.
Okay, it's coming, sir. It's coming. Screen is coming.
Lakshmi Narayana, I will present the screen and explain. Lakshmi Narayana. Lakshmi.
Sir, actually, we are viewing your your
Yes, yes, sir. He joined, sir.
Okay, he joined actually. You shared your screen, sir, not on.
Yes, sir. Yes, sir.
Okay.
1 minute, sir. Sir, Lakshmi Narayana.
Yeah, he joined
Lakshmi.
already.
He has to unmute your mic, sir. Lakshmi, unmute your mic and then you can speak, ma.
Sir,
Lakshmi.
tell me, sir. Tell me, sir.
Okay, ma. I will present. You can start. Sir, we can start, sir.
Yeah, you share your screen. Okay, sir.
Yes. Sir, it is visible, my PPT, sir?
Yeah, it's visible now.
Okay.
Big. Good afternoon, sir. Good afternoon, everyone.
Yeah, you can start. Please go.
Myself, Lakshmi Narayana. I am going to explain about my project, which is solar-powered semi-automated multipurpose agriculture mission. And my teammates are Nara Bharat Kumar, Shailash Rujan, and Naveen Kumar. We done our project under the guidance of Mr. Chadalwada Hamadri sir. Uh, uh, I'm going to explain about the main objective, introduction, and problem statement, and literature review. And the conclusion, the diagrammatic view of our project. The main objective of our project is to reduce the human effort in agriculture field with the use of small mission. Um, you can perform various multiple operations using this mission to increase the productivity and save time. This mission is used to increase the production rate with lesser time, and we are using solar powered as a energy to drive the mission. So next slide. The introduction of our project. Today India in second in world. The main problems faced by our area people are crop monitoring and water resources, input cost, other are skilled labor are the main problems. So to overcome these problems, you are introducing new missions to increase the production rate of agriculture. Um this mission is designed in such a way that you can perform multiple operations at a time, so increase the production rate and decrease it with lesser time. um, I will show the block diagram of our project. The problem statement is to manufacture our machine to perform various operations at a time, and the main you have to convert the solar energy to electrical energy to drive the motors in agriculture field. Mm, the project concept is to propose and develop a portable, lightweight multipurpose agriculture machine. So block diagram. This is our block diagram. Uh, you can see that the solar panel at the top of the machine, and battery to save the energy. And the front of the battery you have seed holder machine. At the top of the holder there is a holder. Here you have one DC motor which is rotate, will give a gap of 3 mm to fall down the seed. At the end of the project you have blade to level the soil, which is 3 level adjustable blade to level the soil. Each level carries 2 centimeter. At the front of the motor you can see the drive motor, which is connected by chain. These are the components you are used in our project. DC motor as a drive motor, 24 volts, 200 rpm. For seed sowing you are using 12 volts, 60 rpm DC motor. For grass cutting, 1000 rpm, 12 volts DC motor. And 2 batteries to store the energy, which is 12 volts, 7 amps. And solar panel of 12 volts, 20 watts. Water pumps to store the water, or pesticide spray. 5 volts relay, which is connected by Bluetooth You can operate it by using mobile phone also, sir. Um, uh, this is water storage tank and a spraying nozzle, adjustable leveler. Each component will be shown next. This is the DC gear motor, sir, which is connected to chain drive. The front wheel, the grass cutter, 1000 with 1000 RPM rotation, 12-volt DC motor is attached at the top of the cutter. And seed sowing, and the green one is the hopper, which you can store the seeds. There is a motor at the middle, which will buffer 3 mm. Thereby you can put one seed.
For class level.
And the adjustable leveler, which each length, it can be adjustable at 3 steps, sir. For each step 2 centimeters you can cover. Next. This is the 5 volt relay with Bluetooth module set up to operate the machine. You can control the machine with the use of our phone itself, sir. And the water storage tank to store the water or pesticide sprayer. Next, sir. This is our component, sir. Solar panel, which is 12 volts, 20 watts, and 12 volts batteries. We are using 2 numbers because the cost of to reduce the cost, you're using 2 volt less watt batteries. Next, sir. This is a circuit diagram of a 5 volt module, sir. Bluetooth module. This is our final proposed work.
Narayana, can you explain about how it will work? That working principle you can explain.
Yes, sir. This can be you have 5 volts Bluetooth module, no, sir. That one app will be available in our mobile. That is available in Play Store itself. You can download it, and if you install it, you can such a device nearby you, means the Bluetooth module you can connect it, and there are 5 different operations for seed sowing, water spraying, and front wheel drive. You can switch on by using mobile itself. Conclusion. This project is used to used for farmers to reduce their effort, and they can perform multiple operations at a time, so they can decrease the input cost. um, uh, th- uh, they can increase the efficiency.
What is the total weight of the machine? I understood. What is the total weight of the machine?
Total weight, sir.
All subcomponent assembly you made, and what is the total weight and total cost?
Total cost is 13,000, sir.
Weight?
Weight I didn't.
Okay. Do you think that your
Because
4 wheels that you have selected would be able to move on agricultural?
yes,
You
sir.
tried it
Yes,
out?
sir. Yes, no, sir. Because You tried in normal, sir, but you didn't try in wet. Normal land, you tried it, sir.
So can it be used for seeding? What kind of seeds you tried? Showing what size of seeds, what land, because there are different types of land.
Yes,
As
sir,
you
sir.
could see, it could be like clay sand, some could be like a red sand, and
Yes,
moving on different terrains, it would be a different challenge if you are going to make low cost machines. Of course, we are happy that you are coming out with a product, but you have to keep all these things in your mind when you are going to design, and when you are going to go for novel
yes,
substitution. Only if it is advisable they would think about using it. Otherwise, the labor is cheap, and if it is for a very small region, this may not be of uh, purpose serving to what agriculturalists need. So you should make a plan and accordingly make the improvements in your project. Okay.
yes, sir.
Thank you. Thank you.
Thank you, sir.
Sir, thank you, sir. Sir, thank you so much, sir.
Thank you,
Actually,
sir.
DE project they have did, sir, and then they completed successfully, sir. But still, whatever you told, further improvements we will try to implement.
Okay. Okay. Thank you. Thank you.
Okay. Thank you, sir.
Thank you, sir.
Thank you very much.
Dharnidhara and Vishwa, are you there?
Sir, yes, sir.
Are you ready to present your work?
Yes, sir.
Mr. Vishwa, now you may share your screen.
One second.
Hello, sir. It is visible.
Yeah, it's visible now. Maximize the screen and start the presentation.
Yes, sir. Good afternoon, everyone. Our research paper is about design, analysis, and topology optimization of connecting rod. Our team are Shanmuga Sundar, sir. I'm myself, Dalitharan, my friend Vishwa, and Sanjay Kumar. We are Sairam Institute of Technology. Then the topic include our abstract, then introduction, then design calculations of the connecting rod, then how we design the connecting rod, then analysis of connecting rod, then topology optimization, then analysis of the optimized design, and the comparison between the existing design and the optimized design, then conclusion. Our paper focuses on the design analysis and the topology optimization of connecting rod. Our main objective is to do a topology optimization in the existing design and to compare the results of the existing design and the optimized design. We have used Creo software for designing the connecting rod and user ANSYS for analysis. Then based on the analysis result, we have done a topology optimization using the Autodesk Fusion 360 software. And again,
your slide has not moved. Move your slide.
Dharnidharan, just maximize your slide. We are still viewing your first slide.
Is it okay, sir? Abstract slide.
Maximize your slide. Just press F5 or show me the slide.
So, sir, can you see the abstract slide?
Yeah, we are seeing abstract.
Okay, sir.
No, you go ahead. Go ahead. No, go ahead.
The topology optimization model is again imported into the ANSYS and it is again analyzed. Then finally, we are compared the maximum principal stress, equivalent stress, maximum principal strain, and the total deformation of the existing model and the optimized model, and it is a final result. Sir. Introduction. We all know that every vehicle which uses the IC engine requires a connecting rod for transmitting the motion of the piston into the crankshaft. The large end is connected to the crankshaft and small end is to the piston. The part which connects is a shank. The connecting rod is exposed to high compressive loads due to the fuel compression. By comparing it with the inertia force are much negligible, so we are not considered it during our design. The connecting rod are manufactured using steel, forged steel, aluminum. In our research, we used steel as the material. And also the connecting rod sections, cross sections are square, rectangular, circular, I section, H sections. In our research, we used I section connecting rod. Though there are various researchers are going in the connecting rod optimization, people are expecting for the best designs. Design calculation, we consider the specifications of the engine.
Sorry to interrupt you.
Yes, sir.
Still, we are seeing abstract slide only. The slide has not moved yet. Yeah, now we are seeing dimensions of something like that. Okay, now it's visible now. Right.
Yeah. Design calculations. Can you see, sir? Design calculations.
Yes, you may continue.
Okay, sir. We have designed the connecting rod based on the specification of the Suzuki engine, which I was tabulated on the right side. Based on the engine specifications, we have designed this connecting rod. This is pressure calculations. By using the gas equations, we find the pressure 15.46 megapascal. And this is for I section of the connecting rod calculation. By using the Rankine formula for bucking load, we have determined the thickness of the I section, and based on the thickness, the width and height of the that is 4T and 5T of the I section are calculated. Yeah, then the small in diameter and big in diameter, based on the force acting on the both end, the diameters of the small end and big end are calculated, inner diameter and outer diameter. This table shows the specification of the connecting rod, like thickness, width, height at the big end, height at the small end. small in diameter, big in diameter, like that. Then the design of the connecting rod will be proceed by my friend Vishwa.
Yeah. Hello, sir. Can you hear me, sir?
Yeah, I can hear you.
Yeah. Yes, sir. First of all, we started designing our basic connecting rod, which are the dimensions we got from the calculations. That is the design you are seeing in, sir. The design is done in the Creo. Design is done in Creo. Then we are send it to for analysis in ANSYS. After the analysis, we got the report from that. So that we got checked that where are the in which of the parts of the load, which are the parts of the canting rod are experiencing less load, but their metals are used in that parts. Then we overgone topological optimization, so that we remove the materials wherever it is not necessary in the parts of the canting rod. Then the next slide, Lenny. Yeah, we had done the topological optimization in Fusion 360, sir, because I think it is one of the software which has this facility, sir, in which we have to specify the constraints where the load is having, where there is a minimum thickness, and what are the materials we can use apply. Based on these values, the software itself check where are the possible areas we can reduce the materials. Based on that, we reduce some materials from our canting rods, so that we can reduce the weight, and also we can reduce. Sir, yes, sir. Sir,
Yes, you continue. Continue.
so that we can reduce material, and also we can also reduce weight, sir, which will definitely improve the efficiency of the machine, sir. That's why we done it, sir. Then next slide, Danny. Yeah, and we also double check after removing the material, so that we can confirm that the material removed container oil is also safe to use in the engines. So we also again performed analysis on the topologically optimized container. That is the image you are seeing in the screen, sir. You can see that there is no performance reduction, but the material reductions you can see in the screen, sir. Okay, next slide then. That's all about this is about the comparison between the previous and the optimized counting loss. You can see the even the stress strain deformations are very close to the values, but the mass is reduced little bit, sir. Few grams we reduced, so that we can, yes, sir, so that we can reduce in all the engines. And if you consider 4-stroke engines, 4-cylinder engines, we can reduce in all the 4 counting loss, sir. This is our graph comparison between the previous and after optimized values, sir. Next then. Yeah, conclusion will be continued by Danny then, sir. Then you may continue, Danny.
Yes, sir. Based on the result obtained from our research, we conclude that the analysis of the maximum principal stress, equivalent stress, maximum principal strain, and the total deformation are less in the optimized design when compared to the initial design, and the weight reduction of about 3.5%. When we applied a force of 39,473 Newton, which is the gas force during the combustion of the engine, based on our calculation. And in our research, we have done the topology optimization in the shank region, which is the region, as I already told, connects the bigger end and the smaller end of the connecting rod. We can done also in other regions, but in this research we have done in the shank region only. This connecting rod can be used for manufacturing, which is lighter weight than the existing region, and also it can withstand the same load, and there will be less stress will be produced than the initial design. These are the previous research works we have referred to, sir. Then these are the references we are used for making our paper. That's all.
Show me the first design and your final design.
Yes, sir. So this is our final design, sir.
What material? Both are of the same material?
Steel. Yes, sir. Yes, sir. Steel we are used. This is the initial design, sir.
Why you wanted to save only 5% of material? This is a simple geometry. Why can't you think of
Yes,
wherever the maximum principal stress along X, Y, Z comes, you can think of increasing the thickness there. Probably in additive manufacturing, you have so much of flexibility to manufacture. So rather than just one geometry that you can develop, think of developing concepts for at least 5, 6. All that you try to compare and come out with a conclusion rather than just taking one single optimized decision, because your Fusion 360 tries to give anything when you just try to give a input. So you
Yes,
will have
sir.
at least 5, 6 concept. Try to evolve a consolidated table for the existing connecting rod and 5, 6, and thereupon come to your final conclusion. Because rather than taking one to one, which is definitely giving you a mild increase
Yes, sir.
in
Yes, sir.
the,
Yes, sir.
do that. Okay, all the
Yes,
best.
sir. Yes, sir. Yeah. Thank you, sir. Thank you, sir. Thank you, sir.
Okay, thank you, Dharmidharan. And I may request our chair, Dr. K. Sandhu sir, to share his few words to the participants.
Uh, I would thank first the management of Sairam Engineering College to keep all the faculty and the other education community to get connected by conducting these kind of virtual conferences. And I'm quite happy that this is the third such series of conference that have been happening in once in every year. And in spite of being in lockdown, in spite of having so much of difficulties in learning, I could see uh, all the undergraduate students, postgraduate students, and research scholars have kept themselves occupied in doing whatever that is possible, and the quality of work was also commendable. And uh, when we start interacting and sharing, it is always platform in which we try to evolve and learn things and augment our work. So I would be happy that all the people who have presented here do not stop with it. And of course, I could find few of the research scholars and all the undergraduate who have presented. Two of the batches do not stop with this. Try to make it into a full-fledged product. And those who are doing the research work, rather than more aptly presenting only the quantitative values, substitute with not only your literatures but also what could have been the reason. So if those kind of things are also included in your technical articles, it becomes easy to publish in very good impact factor journals that are being cited globally. So I wish once again all the very best to all of you, and keep continuing, and probably this bubble would just burst in another few months and we would have a true one face on face interaction on teaching, doing these kind of conferences and all the activities. Wishing you all the very best to all of you. Thank you very much.
Thank you, sir. Move on to vote of thanks. I am very much thankful to all the participants of this conference. This is the first conference in the history of Sairam Institute of Technology, which is completely conducted on a digital platform in line with the social distancing norms due to COVID-19 pandemic. And I sincerely thank our guest, Dr. K. Sannusundran sir, for kindly accepting our invitation. In spite of his busy schedule, he readily accepted our invitation and gracing this event. Thank you, sir. Thank you very much. And we have been fortunate to have some of the eminent persons from academia and industry, and I hope that participants must have benefited by attending this 2 days international conference on materials manufacturing, mechanical engineering, sustainable development. And I thank all the participants and take this opportunity to thank all the reviewers and technical committee members for providing their valuable comments. So once again, I thank everyone whose contribution has made this conference very successful. Thank you, sir. Thank you very much.
Thank you. Thank you.